We are coming to the close of this rather long chapter, and the last bit of thing to diagnose is the what we called before as the Great Cloud Bands. This one has the name SPCZ in the DGF, that is very strong as the northern ITCZ moves south. In the Indian Ocean, it's typically referred to as the marine ITCZ, but you can see, as we said before, even in the summer it remains because the ocean is pretty warm, and then there is a split over here with the monsoon trough getting set up over the Indian region with the orographic rain here and here, Western Ghats and the Himalayas. Bay of Bengal is very warm, and it also remains very active during the summer. So is this part of the ITCZ dynamics? That's kind of a debate that's going on. So some people think of this as a tropical convergence zone, not so much as intertropical convergence zone. But we talked about the very strong pressure gradient here and the lack of rainfall because of the static stability. Looking at the climatology of the Great Cloud Bands, here it is. So distribution of seasonal OLR for DJF and JJA. And there is the South Indian convergence zone, which has a clear presence in the DJF. SPCZ is well known, studied a lot, not studied so much here. And SACZ is also talked about a lot and is very important for rainfall over parts of Brazil, Argentina, and so on here, and has been looked at a little bit. Obviously, when you go to the summer, those weaken. This almost this disappears, and also the SACZ disappears. But you can see that there is a continental rainfall here that may be an anchor, and there is continental rainfall here, maritime continent and Australia, which may be an anchor. We will see that as one of the theories. The same here for the SICZ as well. In the summer, you get another great cloud band here called the Mayu Bayou Frontal Zone, going from China into the North Pacific, again anchored by the East African rainfall. So at least in terms of the processes, maybe continental rain has something to do with these great cloud bands. But the theories obviously have to explain. Sorry about flipping back and forth. My pointer ends up moving the slides. The orientation and the variability have to be explained, but we'll see that there are already some ideas, not a complete list of things. So variability within the Great Cloud Bands itself, focusing again on the Pacific, which has a well-defined SPCZ, or the South Pacific Convergence Zone. You can think of it as the equatorial, tropical, and southern tropical region. So we are looking here at DJF climatology over 1982 to 2008 of 200 hectopascal geopotential height and wind vectors. And here the 200 hectopascal zonal wind with zero contour omitted. Gray shading indicates zonal winds greater than 15 meters per second, and the zonal stretching information. So we are back to thinking about waves, modulation of waves, trapping of waves, energy accumulation, and so on. Okay. Thick line depicts the zero contour. In the lower panel, we have this is the subtropical, not southern tropical. And here we have just the sea surface temperature, which we have talked about before in terms of the winds generating Ekman divergence and upwelling in the East Pacific and piling up warm water and creating the Indo-Pacific warm pool. We are looking at the Pacific side of that. So these blue lines encompass the region where OLR is less than 240 watts per meter squared, which is our magic number for deep convection. So you can see the SPCZ sitting in that, and of course the seasonal changes. Ocean side, there are papers arguing that this orientation is actually related to the zonal asymmetry of the SSTs. But whatever is the theory, I will say again in a minute that it is basically explaining the existence in terms of various theories, not necessarily prognostic, because that becomes a challenge when you want to see how this will respond, for example, to El Nino or global warming and so on. Okay, so you have the upper level winds, the westerly duct that we talked about before, that's clearly seen here, and the mid-latitude subtropical westerlies that are showing up here, with the monsoonal region showing easterlies as we saw before. So you had the invasion of the PVS and eastward advection, etc., that we had talked about before. Zonal winds, you have the core of the trade winds with the du bar dx terms being shown here. Those are contour intervals, so you have negative stretching here and positive stretching here. So du bar dx is positive, du bar dy dx is negative. We're only worrying about longitudinal stretching. Okay, so warm water kind of coincides with the SPCZ, but you know that that's not the complete story, as we have talked about before. This is not the trade winds, as I said before. These are upper level winds, so they are the westerlies. So you have low level westerlies going all the way to the upper atmosphere, and the low level trade winds having the opposite winds as well. Okay, what else do I need to say about that? Let's leave it there. In terms of variability or transients, this is the normalized Fourier spectra for November, December, January, February. That's typically the time period, half the year, where the SPCZ is very well defined and strong. So we are looking at OLR in the equatorial box, the tropical box, and the subtropical box that we marked in the previous figure. So this is showing red noise spectra and the confidence level of 95%, as well as autocorrelations for 0.90, 0.78, and 0.70 for these different regions. Basically shows the decaying time scale. So you can see period in days. There are different peaks in the equatorial region, with one peak here at some I don't know, let's say 40 days, and another one here about 20 days, whereas this one has a peak about more like 50 days, and then this one has no real strong peak except at these high frequencies. We saw that in the northern hemisphere as well, that as we went from 10 to 20 day, 20 to 60 day, and so on, there was high frequency multi-day variability. In fact, in the transients, we looked at the 4 to 8 day oscillations in the eastern Pacific as well, right? The theories of formation, location, and orientation, we go back to the thermodynamic equation, looking at the longitudinal and latitudinal terms and the vertical term with the diabatic heating. So we will basically show that the advective terms and the heating term are balanced differently in the equatorial box, the tropical box, and the subtropical box, and that's what gives you this tilting orientation. Okay, I'm just doing it very briefly because, again, this is a rather consistency check or a diagnostic explanation than a prognostic explanation. We don't really explain why it is the way it is. We just explain what processes are keeping it that way, let's say. Okay, so looking at zonal winds at the upper level, 250 hectopascal and 750 hectopascal, looking at the easterlies in the where are we here? Okay, and the westerlies in the upper levels. So you have westerlies in both lower and upper levels here, and easterlies in both upper and lower levels here. This is the U-bar scale here. So if you look at the latitude longitude section, this is the sign of the latitude. What is being shown is the steady state model results, that same model that we had used before. Zonal wind used in the model containing both latitudinal and vertical shear. So the latitudinal distribution you saw, du bar dy, but it also has vertical shear. Steady state response to equatorial forcing, so diabatic heating is imposed in the equatorial region. Black ellipses show the location of the E-folding magnitude relative to the central value, so kind of a decorrelation scale. Contours denote vertical velocity in red, geopotential in blue, and the C is showing something that we'll come back to in a minute. So this is the decorrelation scale. These are the vertical velocities in red, and blue are the geopotential height. Okay, so remember again that red contours denote vertical velocity. Okay, so you have heating which is dying away within a scale that is shown here, and you obviously have vertical motion and compensating downward motion in both the meridional and zonal direction with these kind of quadrupole structure, which is very typical of simpler models like the Gill model with imposed heating. And you see the geopotential height distribution associated with the heating and the rising motion, where there is positive anomalies and negative anomalies of the geopotential height. So this is consistent with what we already know, and the idea is then to see how the balances of terms in this equation happen in different regions. So C here is showing the schematic of the relative locations of diabatic heating, vertical velocity, and temperature. Results from a series of experiments where the heating was moved progressively poleward into stronger and stronger westerlies. Okay, so what happens when the diabatic heating itself is in a strong zonal stretching region with westerlies. Shaded region denotes upward vertical velocity. Bold contours denote zeros. This is from this paper that you can look up. So in the equatorial box, you have the basic state there being close to zero from prescription, weak easterlies. There is the temperature anomaly, which is fairly weak because you are basically creating vertical motion, which is taking away moisture in response to the heating. So you have strong heating that is imposed and moved in the latitudinal direction into strong westerlies, stronger and stronger westerlies. So in the subtropics, the balance changes for the imposed heating. You get upward motion and a stronger temperature response, but the heating influence dies away. So this is in longitude in that tilted direction. So you are going into the westerly region here and into the stronger westerly region. So you can see that the heating impact is translating into different balances of terms in this equation away from the heating region. So in the tropics, you have a balance between the longitudinal heating and the vertical motion and the heating, the imposed diabatic heating. Whereas if you go off away from the heating along the latitude into subtropics and high latitudes, then the vertical shear term of the advection here and the vertical term of the stability advection you can think of as S bar, which we have defined before as the background static stability, right? So the balance basically changes. So does it say much about the orientation? Not really. It just tells you that the heating is mainly in the equatorial region with convection happening along the band, but the background state and the temperature responses differ and the balance terms differ as you go to higher latitudes from the main source of heating. So you can think of the anchoring heating in the tropics and the extension southeastward in the Great Cloud Band. You can just look at it again and make sure you understand the arguments, but basically the dynamics is trying to fit a consistent story to the orientation that exists.